All right, guys, they're going to look at limits as limits of infinity, or as x approaches infinity or negative infinity, what's happening and what the limit is in that situation. So here we go. All right, limits at infinity. I'm just going to show you a quick example here even before we start. I'm not really going to work it out as much as just show it to you. If I have this function right here, the f of x equals x squared minus 1 over x squared plus 1, and I were to punch it in my calculator and graph it, this is what the graph would look like right here. And what happens is, if you're looking like what happens is the graph goes to positive infinity and also negative infinity, the graph's obviously getting closer and closer to that red line, and that red line is y equals 1. That's going through 1 on the y-axis. It's getting closer and closer to 1. And they're going to use the word arbitrarily a lot today. It's getting arbitrarily close. We did a little table on the calculator just to look what's happened. And I did plus or minus here because everything is squared in the function. So if you plug in a positive number or negative number, you get the same value. So plug in 0, obviously you get negative 1. And then as you start getting larger and larger and larger and larger and larger, the bigger numbers you put in, if you look at the right-hand side there, you're getting closer and closer to positive 1. All right, so what we would say then is we would say, okay, the limit as x approaches infinity, as x getting closer and closer to infinity, that function is getting close. The value of the function, or f of x, is getting closer and closer to 1, arbitrarily closer. We're going to say the limit of that function as x approaches infinity is 1. So the limit at infinity, on the interval from a to infinity, we're not even going left yet, this is positive infinity, is L, means that f of x can be made arbitrarily, there's that word, arbitrarily close to L by taking x sufficiently large. That's a weird thing to say. It really means this in the quotes I have down here. The limit of f of x as x approaches infinity is L. If that is true, the limit exists, if it's actually approaching a certain number. Okay, the geometric representation is the horizontal asymptote. Think about way back when we did those horizontal asymptotes. I gave you the 3 rules, all right? And I made a big deal about the horizontal asymptote really tells you what's happening at the ends of your graph. Like if you look at this first picture, that graph's getting closer and closer to L, the red line L. Here, that looks like exponential decay, getting closer and closer as we're going to infinity. That's the horizontal asymptote. This is a little bit different kind of picture, but still, as you're looking at it, you know, going closer and closer to infinity. It's going to the right forever. It's getting closer and closer to that line, which we're going to say is line L. Okay, so horizontal asymptote, huge hints on limits as x approaches infinity because they tell you the end behavior of your graph. It tells you what's going on at the end of your graph. All right, let's go negative infinity, limit at negative infinity, just go in the opposite direction, okay? You probably can't see this box, but in here it says the limit as x approaches negative infinity. So now we're going to the left. And it says the same thing at the bottom. It means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large negative. All right, so if you go way to the left of your graph, you go closer and closer to negative infinity, you know, and it's approaching a certain number. It's approaching this line. It's approaching the horizontal asymptote. All right, again, then that limit exists, and the limit would just be L. All right, the horizontal asymptote, here we go. The line L is called a horizontal asymptote of the curve if, I just messed up my graph, if either you go to positive infinity and you get L, or you go to negative infinity and you get L. Either way, if that happens, if that limit exists, then you have a horizontal asymptote. And what I've done here is I've graphed the inverse tangent graph. This graph is this. It's I should have done y equals inverse tangent of x. Think about the tangent graph we used to look at, and then flip it sideways. Your x's becoming your y's becoming your x's. That's what inverse tangent looks like. And if you look at it, it's getting close. As you go to the right, the graph's getting closer and closer to positive power 2. As you look at it going left, it's getting closer and closer to negative power 2. So the limit as x approaches negative infinity of the inverse tangent graph, or inverse tangent, is negative power 2. And the limit as x approaches positive infinity of inverse tangent is positive power 2. Right? And that's just how we write it. Okay, find the limit as x approaches positive infinity of 1 over x, and also as it approaches negative infinity of negative x. Now, if I start putting positive numbers in for x, let's say 1 over 100, 1 over 1,000, 1 over 1,000,000, All right, what's happening is that approach is getting closer. Is it getting arbitrarily close to something, the larger number I put in? And the answer is yes. It's getting, the value of that fraction is getting closer and closer to zero. And look at the graph here. I graphed it also, and the graph also, if you're looking towards positive infinity, it's getting closer and closer to zero. So we would say, okay, the limit as x approaches infinity of 1 over x is 0. Let's do the same thing with the negative here, with the negative side. If I start putting in large negative numbers like negative 100, negative 1,000, this is what I'm getting, negative 1,000,000, then the question becomes, what's happening to that, to the value of the function? The answer is getting closer and closer to 0 again, arbitrarily close to 0. Look at the graph. As the graph is going left to infinity, it's also getting closer and closer to the x-axis, which means the limit as x approaches negative infinity of 1 over x, that's our function, is also 0. Okay, both of those are 0 because they both approach 0 as you get closer and closer to infinity as you use arbitrarily humongous numbers. All right, so here's our rule. This is a big one. Make sure you get this down. If k is any positive integer, then the limit of 1 over x to any power, as long as it's positive, and it's an integer, it's got to be, you can't put in like 1.2. It's got to be like 2, 4, 8, 7, 5, whatever, some kind of positive integer. As it goes to positive infinity or negative infinity, you're going to get 0 for that limit. That's a big deal. It's going to help us a whole lot finding limits here in just a minute. So 1 over x to any power, the limit's going to be 0. Okay, let's work one out. Okay, what I'm going to do today a lot is I'm going to use that property we just saw on the last slide. And I'm going to rewrite all these limits to where I have like 1 over x or 1 over x squared and stuff like that. So what I'm going to do first with this limit that they gave me on the slide is I'm going to divide everything up there by the biggest degree. Like x squared is the biggest degree. So I'm going to divide the first term by x squared, the second term by x squared, the third term by x squared. Same thing on the bottom. Divided by x squared. And this is legal because I'm doing the whole thing by x squared. That makes it completely fine. All right, now if I do that, I'm going to get here. I'm going to get the limit as x goes to infinity of just 3 minus 1 over x minus 2 over x squared. And then on the bottom, I'm going to get 5 plus 4 over x plus 1 over x squared. Now, because I have all this in my numerator, all this in my denominator, I'm going to split it up into separate limits. Remember, if you have things that are added together, limits that are added or subtracted, you can break them up and do each individual. So here we go. Saying limit of, as x approaches infinity, 3 minus the limit as x approaches infinity of 1 over x minus the limit as x approaches infinity of 2 over x squared. Same thing on the bottom. I know it's a lot. Hang in there. X infinity is 5 plus the limit of x approaches infinity of 4 over x plus the limit of x approaches infinity of 1 over x squared. Now, here's the deal from the last slide. Take each one of these individually. As x, if it's just an integer, if you just have an integer or a constant there, the first one, that's just 3. All right? What we just learned on the last slide is if you have any of these functions where it's 1 over x squared, whatever, and you have an integer k for an exponent, then it's just 0. So the next one is just 0. The next one is just 0. On the bottom, same thing happens. 5 is a constant, it's going to stay 5. That one, because there's x in the denominator, it's going to be 0. This one, x in the denominator with a coefficient, sorry, with an exponent of 2, which is an integer, is also 0. So my limit ends up being 3/5. There's the limit as x approaches infinity of that function, 3/5. Hope that makes some sense. We're going to do that a lot, breaking them up like that. All right, last slide. Thanks for hanging in here today. Quite a bit of stuff. It says use numerical and graphical methods to find the limit as x approaches negative infinity of each of the x power. Now, that's an exponential function, and we've graphed a lot of exponential functions this year. Remember, e is like 2.71828, so it's exponential growth. And what I've done down here is I've taken a picture of the graph of y equals e to the x. Now, don't forget, we're going x as x approaches negative infinity. Okay, so it means we're going left. So graphically, you can tell by the picture exponential growth as you go to the left, as you're approaching infinity, it's getting closer and closer to the x-axis, which is 0, by the way. And what I did here, I took a picture of the table, just plugging in, because again, we're going to negative infinity. More and more large negative numbers. As you see what's happening, as we start with 0 and then go just to negative 10, look where we are at negative 10 already, like 0.000005. So, if you do negative 100, it would be even less than that. Your calculator's going to give you a bunch of E negative stuff on your calculator if you start punching that in. So anyway, both cases, the limit's approaching 0. So we would say the limit as x approaches infinity of e to the x is going to be 0. All right? Hope that makes some sense. And we'll work on it in class tomorrow. See you then.